Now, that was my reaction first time I got to infinite series. It is so tough. First of all, let me open this document. And I sent this document. This is a document from my other calculus book, which actually treats infinite series in much more detail and in length so that you actually have a chance of understanding it. To be honest with you, the book that you have and that I also have that covers Chapter 9, I don't know how anybody could learn infinite series from that book. It just does not do a good job of explaining these things. There are basically 10 tests for convergence. Okay? And this goes over on my... Can you read these from my page that you're looking at here?
Yeah, I can see them.
Okay, good, because I can't blow them up and have them all on there. But you pretty much, when given an infinite series, you pretty much want to start at the top and work your way down.
Yeah, she gave us like a little flow chart explaining that today too.
Okay, I know the book has a flow chart in there, and I don't like that either. I didn't find that flow chart in the book helpful at all. Here's the problem. The problem is we could probably spend a half an hour on the nth term test. We could spend an hour on geometric series, at least an hour on telescoping series, and so forth and so on.
What are telescoping series? I haven't heard that before.
That's where you have a factor in the denominator. You have something like 1 over x minus 1 times x plus 1. Or n plus 1, n minus 1. They're actually fairly easy. I'm not sure why your book doesn't cover them. I noticed that none of the problems you sent me had telescoping series in there.
Yeah, she's made no mention of it.
It's one of the easier ones, but it's something certainly we don't need to talk about because there's so many others we do need to talk about. P-series, those are the next most important. So I would say nth term test first, geometric series, and then P-series, and then all
P-series I get pretty well.
P-series, we've talked about those, and geometric series, I know you've had that. Alternating series, these are pretty interesting and pretty easy. It's pretty easy for an alternating series to be convergent. It only has to have 2 qualifications. One has to pass the nth term test. In other words, the nth term has to be 0. And 2, the nth term has to be greater than the nth plus 1 term. In other words, it has to be a decreasing series. For example, I don't even know where to start today, but we know this series is divergent, right?
Yeah.
That's 1 over n. In other words, it's a p-series where p is 1, and that's why it's divergent.
So the requirements are that it's approaching 0, and let's see, what was the other one?
Well,
and that it alternates.
Right. In other words, this is a divergence p-series. However, if you have the alternating series of the same series, it's convergent. And the only thing I have to prove that that is convergent is, first of all, the nth term has to be 0, and we can tell that it is. It's an alternating series, and once we discover that it's an alternating series, the only thing that matters is that part right there. And the only thing left to determine whether it's a convergent series or not is whether 1 over n is greater than or equal to 1 over n plus 1. And it always is. notice that when n is 4, this is 1/5, 1/4. 1/4 is always bigger than 1/5. So we have a series that's headed to 0. The nth term is 0. And every term is getting smaller. That's all you need to make an alternating series convergent. Notice that that works on that first series also, but that's not an alternating series. That's a p-series. So that has to follow the p-series rules. So it's easier for an alternating series to be convergent than it is for the non-alternating series to be convergent. That's divergent. But the same series, as long as you make it an alternating series, is convergent. And this also gets a little bit to the heart of when we're talking about conditionally convergent or absolutely convergent. This series, this harmonic series, 1 over n, is conditionally convergent. It's not always convergent. In other words, if I remove the alternating part of it, it's not convergent anymore. So it has to be an alternating series for it to be convergent. And that makes it conditionally convergent. Okay, let's say I made it 1 over n squared for both series. Now, the top series is a p-series where p is greater than 1. That makes it convergent, right?
Mm-hmm.
The bottom series, well, for sure, that is true, that 1 over n squared is greater than 1 over n plus 1 squared. That's what has to be true. In other words, this is a decreasing alternating series. Because this is convergent and this is convergent, this is absolutely convergent. It does not need the -1. It doesn't need to be an alternating series to be convergent.
Okay.
So the harmonic series is an excellent series to illustrate the difference between absolute convergence and conditional convergence. But let's not get there quite yet. Like I said, to do a proper job on this, we would need much more than a few hours. The integral series. Have you done that one?
Yeah, I think so. I could use a refresher on it, though.
Well, as long as you can express this series, a sub n, as a function, and if you integrate it and it goes to a number, it's convergent. Doesn't matter what the number is, even if it, if, in other words, that's the area under the curve between 1 and infinity, right?
Mm-hmm.
Well, if the area under the curve is convergent, it will go to a number. So that when you take the integral of your function and evaluate it, and if you get a number, it's a convergent series. If you get infinity, it is not it's a divergent series. Notice the very top, conditions of convergence is this column, conditions of divergence. All right. The last 4 tend to be some of the tougher ones, but the ones that you need to use for a lot of the tougher problems. The root and the ratio test. I'm sure you've had the ratio test, but I didn't see the root test in your book.
Yeah, we've had a lot of the ratio test. Nothing about roots, though.
Right. The ratio test is a great one, and it's used in a lot of the problems. I had to use it in maybe half the problems you sent me. And it's a measure of absolute convergence, actually, even though this table doesn't say so, because you're taking the absolute value. Do you have any questions about what this means when they say a sub n plus 1 over a sub n?
I understand the execution of it. I don't quite get the why of it.
We'll get a lot of problems that use the ratio test today, so let's wait on that. Direct comparison and limit comparison. These tend to be the hardest, mainly because in order to use direct comparison, you have to think of the series to compare it with. And that's not easy. That takes a certain amount of creativity. And limit comparison is comparing your series, the one that's here, with another series similar, and if that limit is greater than 0, then and the second series converges, then the first one converges. These get very complicated. And having 10 of them doesn't help, but it actually does. Like I said, in an ideal world, we'd have an hour to review each of these and review series that we use each of these tests on. But since we're speeding it up a little bit, the next step in analyzing infinite series is determining which tests to use on these functions. And you probably would agree with me that that's where the difficulty lies.
Yeah.
In finding out which tests to use. Well, if you don't mind, let's go through these 7, because this is kind of like the beginner slope if I was teaching you to ski. Whereas the problems you gave me is more like the intermediate and the expert slope. So when I first looked at these this morning, I realized that it had been so long since I've been involved in this that I was lost. So I had to go back and review my books, and this page was the one I always wanted to go to. Because the first time I was learning this page was the key page to me. Each one of these 7 uses a different test. And being able to figure out which test to use on which series is half the battle. Okay? So, let's start with A. Any idea on how to do that one?
No.
Where would you begin? What's the nth term?
Where would I, let's see.
Here, let me put some writing space on here. Remember how you get the nth term. In other words, what we want is the limit of n plus 1 over 3n plus 1 as n goes to infinity. If that is 0, then it might be a convergent series. If it's not 0, question answered, it's a divergent series.
Yeah.
No further work needed. So, go back to your limits. When you first started calculus, they started you off with limits. What happens when I have a variable in the numerator and a variable in the denominator that are the same degree, and I'm letting the variable go to infinity? What is the limit?
Let's see, you divide the coefficients, wouldn't you?
Right, the ratio of the coefficients.
So, yeah, 1/3.
Okay, that's not 0. It's divergent, end of problem. So I would say kind of always start out with the nth term test. If you don't know where to begin on a series, begin on the nth term, because you make the answer almost immediately, like this one.
In the nth term test, if the limit's anything but 0, it diverges?
Yes.
Okay.
If it's 0, doesn't make it convergent. In other words, if I have this series, the harmonic series, the nth term is 0, correct?
Yeah.
But it's not convergent.
Yeah, clearly going to diverge.
So, well, it's not clearly divergent, but it's divergent
clearly.
because it's a p series and p is 1. That's why it's divergent. If I make p 1.01, that's a convergent series. It's a convergent p series because p is greater than 1. So if p is less than or equal to 1, it's divergent. But this passes the nth term test. We can't know that that's divergent because the nth term test is 0. So it only works one way. It's not an if and only if. Let's look at B. The next most, do you know this one?
No.
What have I told you that is a geometric series?
Then we'd have to find the common ratio, correct?
What is it?
Would we have to find the common ratio then?
Yep.
Or the...
Well, we got to find out what R is. In other words, the geometric series is basically R to the n. And it's only convergent if the absolute value of R is less than 1. Well, what's R here?
Pi over 6, which is less than 1.
That's a convergent series.
Okay, and by what test is that?
The geometric series test.
Geometric series test?
Yeah, I sent you both of these documents in an email right before the session started.
Yeah, I got those.
And so this is a really good one to have. Better than the flow chart. A lot better, in my opinion.
She gave us a sheet as well. It looks like she took off telescoping.
Okay, that's fine. It doesn't have to have all 10. And in fact, I'm not sure that there's only 10. It may just be that my book only covered 10. There might be 20 or 30. Who knows? But my book covered 10, and this table has all 10 of them. The geometric series has another big advantage. There's the geometric series. It's actually a times r to the nth, but you can always take that a outside the summation sign. Constants for series are just like constants for integrals. If it's a constant, you can put it outside the integral sign. If it's a variable, you cannot. Same thing with a series. In other words, this one that they show here is the same thing as a times the sum of r to the n. The advantage of geometric series, which is a big advantage, is that it also, you can figure out what it converges to. It converges to this thing over here. S, the sum, is equal to a over 1 minus r. So in our problem that we just did, even though it doesn't ask for it, the sum would be a over 1 minus pi over 6, which was r. And a was 1. In other words, there was no number there. So whatever that number is what this series converges to. Notice that not many of these tests tell you anything about what it converges to. The geometric series does, the telescoping series does. But most of these, they all talk about remainders and nothing about what it converges to. So the name of the game tends to be, does it converge or does it diverge? Once you get past this, and you have problems that talk about the radius of convergence and the interval of convergence, that's when you start paying more attention to the geometric series. In other words, if I replace r with some variable, we might as well talk about that now too. If I told you that x over 2 to the n power, is that convergent or divergent?
Divergent, right?
We don't know. In
I
other
guess,
words,
yeah, with x.
it depends. The absolute value of r has to be less than 1 for it to be convergent. So I could say the absolute value of x over 2, as long as that's less than 1, I'm going to have a convergent series. And now to solve that, I get the absolute value of x has to be less than 2, which means x has to be greater than minus 2 and less than 2. So its radius of convergence would be 2. As long as x is between minus 2 and 2, then this quantity is less than 1. And that quantity needs to be less than 1 to even talk about this as a series. Have you seen by now, divergent series are not even numbered. They're outside of the domain. If I gave you this series and I said, what's the domain of that series? It's minus 2 to 2. This series makes no sense whatsoever if x is 3 or 4 or anything bigger. It's a divergent series. It's only worth talking about if it's a convergent series. And so we get into this radius of convergence. Well, the radius of convergence here is actually 4 because it goes from minus 2 to 2. Now let me take that back. The radius of convergence might be 2 here. I'd have to look that up. You also have the interval of convergence, which is different than the radius of convergence. I know that my interval of convergence is minus 2 to 2 in that problem, but I don't know if it's convergent at the endpoints. So it's not even fair to call this an interval of convergence. This is the interval over which the function converges. But without checking the endpoints, it could be that. It could be this. Or it could be a right bracket and a left paren. And we would have to check each point, and it's going to be different for different series. So the radius of convergence is how wide x can be. The interval of convergence tells you over what numbers it is, but the actual definition of interval of convergence also tells you whether the endpoints, whether it's convergent at the endpoints. All right, let's go on. Otherwise, I'm never going to get this material covered here. Number C. Notice that if I use the integral test is a test that can only be used if you have an always positive function that's always decreasing. Okay? And you have to be able to write it as a function, well, y, and it's between 1 and infinity, and in places of n, I make it x, because I'm going to integrate this thing. And if my integral is a number at all, means the area under the curve is finite. I mean, that's what this thing means, is if I integrate it from 1 to infinity, I'm getting the area under the curve between 1 and infinity. If that's infinite, then it's a divergent series. If it's finite, it's a convergent series.
Makes sense.
Okay. Now, why is this a perfect series to use the integral test?
Couldn't tell you.
That is very easy to integrate using U substitution. Notice that when you use, this might be taking you back a way, I don't know. I don't know how anybody goes from pre-calc to calc BC and learns it, because it's just next to impossible. No, seriously. I mean, they have no right, they have no business doing that to you, first of all. Nobody should be taking calc BC that hasn't taken calc AB. Now, if you took a full semester of calc AB as part of your pre-calc course, maybe that's different, but notice that when we are integrating, if whatever the inside is, which in this case would be minus x squared, if the derivative of the inside is the multiplier, then it's perfect for integration. Notice that du dx would be equal to minus 2x, which makes du equal minus 2x dx. And now I can turn it into an integral in u. I've got, well, I don't have a 2 in front of that, or a minus, but I can take care of that. I'll put a minus 2 in front of that and a minus 1/2 out there. Now I didn't change anything. I don't know if they taught you that technique or not. There's a couple of ways to do these U substitutions. But if I do that, now I've got the minus 2x and the dx that can be replaced by du totally. So my new integral is e to the u du. Well, I know how to integrate that. What's the integral of e to the u du?
E to the u du. It's been a while since I've done this.
It's e to the u.
Yeah.
In other words, e to the x is the only function whose derivative is the same as the function, which means the integral is the same as the function. So once I turn it into an integral of u by doing this u substitution, now I can say, well, okay, so there I still have my minus 1/2 in front, and now go back and resubstitute the minus x squared for u. So the answer to this integral is minus 1/2 e to the minus x squared. Now, if I evaluate that between 1 and infinity, you know how to do that?
Between 1 and infinity?
In order to use the integral test, that's what you're always doing. You're always evaluating it from 1 to infinity. Well, what does that give me? That gives me minus 1/2 over e to the infinity minus a minus 1/2 e to the minus 1. And then we're going to take the limits of that. Well, the limit of that is 0, because the denominator blows up. But the limit of that is a number. In other words, there's no unknown variable over there. That's plus 1 over 2e. That's a number. Since the integral came out to be a number, that is a convergent series. If the integral would have come out to be infinity, that means the area under that curve is infinite. That's an,
Divergent. 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 Diver
And this is something that maybe isn't obvious to you yet, but it's quite interesting. There's the curve 1 over n, or 1 over x. Asymptotic with the x-axis, right?
Uh-huh.
If I integrate this curve between 1 and infinity, I get an infinite area. Okay? That's 1 over x. That's a p-series. We know that's divergent, so I would expect to get an infinite area. If I make it 1 over x squared, it doesn't change the curve much. I'll write it in blue. 1 over x squared is something that looks like this. Still is asymptotic to the horizontal axis. But guess what? The area under that curve between 1 and infinity is finite. Which brings up the question, how can it be finite when I'm going to infinity and it never touches the x-axis? But it is. I don't know if you ever came across a problem called Gabriel's horn.
Not yet.
You did?
No.
Okay, well, Gabriel's horn presents a very, very interesting problem that if you take this curve, the red curve, and you revolve it around the x-axis, you create a three-dimensional object that is called Gabriel's horn. And what is interesting about Gabriel's horn? It has a finite surface area, it has a finite volume, but an infinite surface area.
Huh.
And think about that for a while. Has a finite volume, because you break it up into disks. Each disk is pi r squared. And when you sum up all those pi r squareds, the fact that it's squared makes it finite. It's a convergent series. So the volume of Gabriel's horn is finite. But if you were to figure out the surface area of it, it's infinite. Because surface area is based on this series. So you have a horn that you can't paint because its volume, in other words, if you filled it up with paint, it wouldn't be enough paint to paint the inside of it. So it's a bit of a paradox. And Gabriel's horn isn't the only one that's a paradox. There's all kinds of three-dimensional solids that you can create that have finite volume and infinite area. Sounds like it would be impossible, but it's one of the more interesting things in calculus is Gabriel's horn. All right, let's see. So anyway, the ability to recognize that as a function that can be integrated easily is very important. If that series were n squared times e to the minus n to the squared, I can't use the integral test on that because I don't know how to integrate that. In other words, there's a lot of functions that you can't integrate, at least not easily. And so I would not apply the integral test to that because I can't integrate it. But noticing that I can integrate it as long as that's just n is all the difference in the world. So on this one we use the nth term. This one was a geometric series. And this one we use the integral test. Now, let's skip D for a moment. We'll come back to it. E. I kind of want to go in degree of difficulty here. What kind of series is E?
Alternating.
What's the nth term? Okay, so therefore, there's only two conditions that I have to prove that make it a convergent series. Okay, one is the nth term has to be 0. Is that true here? And incidentally, this is the series. Take that out. In other words, if I'm talking about the series here, it's 3 over 4n plus 1. When we're applying all of our tests to determine whether it's convergent or divergent, this is a sub n without the minus 1 to the n. Minus 1 to the n merely tells us that it's alternating. So, how about the nth term test? That's the first thing. What's the nth term?
3, right?
No, this is the nth term as n goes to infinity. What happens as the bottom goes to infinity?
It'll approach 0.
So the nth term test, it passes. Now, the only other thing we need to prove convergence of an alternating series is that each term gets smaller and smaller. In other words, the nth term has to be less than the nth plus 1, less than or equal, actually. If I had a series where it was getting smaller and smaller with every term, this would be true, right?
Mm-hmm.
Well, the nth term is 3 over 4n plus 1. Is that smaller than, well, what's the nth plus 1 term? 3 over 4 times n plus 1 plus 1. Hold on. If I have this backwards, I might have it backwards here. The alternating series, a sub n has to be bigger than a sub n plus 1. I got it backwards. A sub n has to be bigger than or equal to a sub n plus 1. Well, notice that this denominator is always bigger than this denominator. Their numerators are the same, but this denominator is 4n plus 5. This denominator is 4n plus 1. So this term is always going to be bigger than the next term, the nth plus 1 term, which means it's a decreasing series. Every term is decreasing. And if you have an alternating series where every term, successive term is decreasing, that passes the test for convergence. And that's true with that series right there. Passes the test for convergence.
By the comparison test?
No, by the alternating series test. Notice what the alternating series test says.
Yeah.
The limit of a sub n has to be 0. That's the nth term test. And a sub n has to be bigger than a sub n plus 1. And they both have to be bigger than 0. In other words, but that's true in this case. In other words, the nth term goes to 0, and the nth term is bigger than the nth plus 1 term. To figure out what the nth plus 1 term is, you just substitute n plus 1 wherever you see n.
Okay.
Okay. Let's look at F. Now, you don't really need much information to figure out F. When you have factorials, the ratio test is a great test to use. But the fact of the matter is I don't need it here. I've got factorial in the numerator, I've got exponential in the denominator. Which grows faster, factorial growth or exponential growth?
I'm not sure.
Factorial.
Factorial?
Mm-hmm. In other words, if I told you, you know what 50 factorial is?
No.
Like 10 to the 64th power. That's how fast factorial grows. So if I had factorial growth in the numerator, no matter what I have in the denominator, as long as it's exponential, I could make that 1,000,000. But I could make it 1,000 certainly to the nth power. This is exponential. This is factorial. It'll take a while, but the factorial growth will eventually catch up with and surpass the exponential growth, no matter what this number is. Even if that number was 1,000,000,000, would not matter. So whenever you see factorial in the numerator and exponential in the denominator, that's a divergent series. Reverse it,
Convergent.
and it's going to be well, I'd have to maybe prove that it was convergent. I know the nth term is 0, but what I would then have to prove is to make sure the nth term was greater than the n plus 1 term. And that's, I want to make sure we get to that. Because there's some tricks with this factorial when you use the ratio test that are not obvious at all. For example, let me just cover it now. If I have n what's that equal to? N plus 1 factorial divided by n factorial. Put in some n. Put in some n. Put an n of 6 in there. Now you have 7 factorial over 6 factorial, which is equal to what?
7.
So that's n plus 1. And it doesn't matter what n you put in there. If I put an n of 10, then I have 11 factorial over 10 factorial. That's 11. That's n plus 1. So n plus 1 factorial divided by n factorial is n plus 1.
Okay.
And that is key whenever you're applying the ratio test, because you always have this. And one of the things to look for to apply the ratio test is when you see factorials or even exponents to 1. Let's see what it said with this. Yeah, we can apply the ratio test to this. Let's do it, just so I can show you what I'm talking about. Because that's, in other words, it's one thing saying factorial growth outstrips exponential growth, and therefore that's divergent. But if it was the reverse, I wouldn't be able to prove convergence without doing more work. So the ratio test is, I'm going to put a sub n and divide it by a sub n plus 1. I'm going to take the absolute value of that and take the limit of it as n goes to infinity. If that is less than 1, it's convergent. If it's greater than 1, it's divergent. If it's equal to 1, it's inconclusive. Well, let's do it for this problem. Here's n factorial. In other words, this part here is n factorial over 10 to the n power. I'm going to divide that by a to the n plus 1. Well, that's n plus 1 factorial divided by 10 to the n plus 1. So I have a fraction divided by a fraction. The ratio test always comes down to multiplying by the reciprocal of the bottom, right?
Mm-hmm.
So this problem becomes this. I'm going to take the absolute value of that, and I'm going to take the limit of it as n goes to infinity and see what we get. Well, notice that 10 to the n plus 1 over 10 to the n is what?
10.
Yeah,
right?
10 in the numerator. So I can cross that out with that. And in the denominator, I have n factorial over n plus 1 factorial. That's n plus 1 in the denominator.
Okay.
So what does that go to as n goes to infinity? In other words, now we're looking at this. As n goes to infinity, what does this limit go to?
0.
Since 0 is less than 1, that is a convergent series. Hold on. It's not a convergent series, it's a divergent series. I got something backwards here. Ratio test. I got it backwards again. It's n plus 1 over a sub n. I did a sub n over a sub n plus 1. So if I reverse this, I'm going to end up with 10 in the denominator, n plus 1 in the numerator. The limit of that is infinity. It's a number greater than 1. That's why that's a divergent series. I apologize for getting these backwards. It's just because I don't have this page memorized perfectly. That's why I think it's a wonderful page, is because when you're working with these, you're always having to go to this page. When I'm doing these problems, I'm pulling this page up all the time because each of these tests has slightly different conditions. All right. So they actually did this problem by using the ratio test. Now, G. When you have n taken to the nth power, usually when you have anything taken to the nth power, it's a candidate for the root test. And yeah, when it involves a variable that is raised to the nth power, indicates the root test may work well. And after applying the root test, you will conclude that that series converges. Since you haven't had the root test, I won't do that one. You can get a brief peek at what the root test looks like. It's when you take the nth root of the series as n goes to infinity. If that's less than 1, it converges. If it's greater than 1, it diverges. But it has to do with taking the nth root of whatever the series is. All right, let's go back and look at the one that I consider maybe the hardest on here. And that's D. 1 over 3n plus 1. Notice what it says. The nth term is certainly 0, right?
Mm-hmm.
But it's not an alternating series. So having the nth term be 0 merely doesn't tell us anything. It can still be either convergent or divergent. So we want to compare it to a known divergent or convergent series. Well, if I look at that, 1 over n is the closest thing to looking like that, right? So and I know 1 over n is divergent because it's a p-series. It's the harmonic series. So by using the limit comparison test and using this, in other words, this is tough because I have to first figure out the series that I want to compare it to. And usually when you're doing a direct comparison or a limit comparison, try to find a common series that you're kind of familiar with. And 1 over n, we're certainly familiar with that. Well, if I'm going to use a limit comparison, I'm going to compare, notice the bottom, what it says. It says I'm going to take the limit of my series, which was 1 over 3n plus 1, and I'm going to divide that by a known series, 1 over n. And if this limit is greater than 0, then my series does the same thing as the known series. If this limit is that's it. If the limit is greater than 0, then it does the same thing that the known series does. Well, to take the limit of that as n goes to infinity, I'm going to flip and multiply, so it's times n over 1. And now that series is n over 3n plus 1. What does that go to? As n
1/3.
Since 1/3 is greater than 0, then my series a sub n does exactly the same thing that b sub n does. It diverges. If I was comparing it to a convergent series and my limit came up to be greater than 0, it would be convergent. It's going to be, so all this limit comparison test does is tells you that it does the same thing as the series you're comparing it to, which makes it tough because you have to come up with what that series is. All right, let's see if we can have a quick look at some of your problems here. But I would recommend that you refer back to this page a lot because we have 7 different series and 7 different tests to apply to them. And the telescopic one is missing. So most of the tests that you've had can be, you can learn a lot by looking at these specific problems. Now, I did all of the problems 29 through 43, which merely ask you to determine convergence or divergence, and you have to identify the test. In other words, these are just like the 7 problems we just did. You got to just identify the test. Okay. We don't have much time. Let's do 29. I think I can do 29 in 4 minutes. What's the nth term test tell you?
Limit equals 1, right?
So what is that series? Divergent or convergent?
Divergent.
Immediately. That's the beauty of the nth term test, is if it's a divergent series, you find out immediately with very little extra work. Let's look at 32. Only because we're running out of time and we need quick problems. Notice what 32 is.
Is that p-test?
No, it looks like it's a p-test. It's really a geometric series. In other words, I can take that negative sign and put it out there. Leaves that behind. Same thing. And now here's the key. I mentioned this in our last meeting. That's also, because the numerator is 1, I can make that n apply to that whole fraction. That is the same as that. Notice that 1 over 8 to the nth power is the same as 1/8 to the n. Because 1 to the n is always 1, no matter what n is. So, and this is something you have to see. You get a lot of series that put a 1 in the numerator. They put the n as an exponent in the denominator, and you have to make this leap. Once I've turned it into that, what am I looking at now?
I'm not sure.
Geometric series.
Geometric. Oh, because r is less than 1.
Right. In other words, always try to see that one.
Yeah.
R, and there's an a in front of it. And in this case, our a was actually -1. Okay, but our r is clearly 1/8. So if there's any series that you want to recognize more than any other, it's the geometric series. For one thing, not only are a number of these problems going to use the geometric series, but the geometric series is what most of your problems that talk about radius of convergence and interval of convergence use. Because only the geometric series can you make progress at figuring out what it converges to. In other words, I know this series converges to -1 over 1 minus 1/8. That's what it converges to. And if I had an x in here instead of a 1, in other words, if I introduce a variable, now I know that it only converges as long as x is between -8 and +8. My inside still has to be less than 1. And that's when you get into radius of convergence, is when a variable besides n is introduced into these things. Notice that none of these have any x's at all. They're all n's. Each one of these is just a infinite series with n is the only thing, and it's counting up from 1 to infinity. Well, the moment I introduce a variable, it kind of changes the game, because now there's only certain x's that make that series convergent. I don't even want to talk about any of the others. When x is 9, there's no point in discussing the series. It's not convergent, it's divergent. All right. I guess I'm going to have to go, and I'm sorry we didn't cover much of the material you sent me, but in all honesty, I think in your best interest, what we covered was more important.
I agree.
You kind of have to start somewhere with these series. I mean, you just can't start on the expert slope and figure out, you know, I got to use the ratio test on this one here. Although there is some clues on 37. I'm going to use the ratio test because I see factorials and I see n as an exponent. That's a great clue for using the ratio test, because those factorials tend to cancel one another out when you put an n plus 1 in there. Same with the exponents. So there are certain series that you want to recognize instantly. What's the nth term on 38? Recognize that?
No.
E.
E?
Yeah. The definition of E is the limit of 1 plus 1 over x to the x power as x goes to infinity. That's E, which is like 2.71. So if I try to figure out the nth term there as n goes to infinity, that nth term is E, which is not 0. That is a divergent series because of that.
Okay.
All right, Nick, I will let you go. And good luck. That's all I can say. This is hard.
Thank you.
This is really hard material. The only thing I can say is you will not be in a minority if you do poorly on the test.
Thanks for the reassurance.
I would almost be willing to bet you that less than 10% of the people in your class pass this test unless he grades on a total curve. And then you may be totally different. But nobody else is going to get this stuff either, believe me. All right?
Good to know.
Yeah.
Thanks, David.
All right, Nick.
Have a good one.
Bye-bye.